This is lecture number 11. In this lecture, we're going to give an introduction to feedback controls. That's the next part of this unit. We're going to be talking about control systems. And so this is the second unit in this course, and this is actually talking now about design. So the fundamental control design problem involves finding a practical way of affecting a given system so that it adequately accomplishes the required maneuvers. This must be done in spite of an inaccurate model of the system and the presence of interfering disturbances. So we start off talking about practical. I like to make things as practical as possible. There's a lot of control systems that's all theoretical, and so I'm not so theoretical. I mean, I can do the theory, but for you all, I want it to be practical. I want you to be able to use this. So a practical way of affecting. So the affecting is the actual control process. And if you think about what's actually going on, basically, if you have a system given by a transfer function, continuous time transfer function, you've got basically a differential equation that underlies that transfer function. And so the control basically is a way of modifying the behavior of that differential equation. So that's the basic concept behind it. But so affecting a system, you can think of it in terms of the differential equation or in terms of other ways. But basically, we want to affect the system. Okay, and so affecting a system so that it adequately. So when we talk about adequate now, there needs to be some kind of measure of what constitutes adequate. Okay, so we need to talk about some of these issues. Accomplishes the required maneuver. So oftentimes when you have a design problem, you have design requirements. That is, it has to meet these certain things. It has to do this. It can't do this. Those kinds of things. So required is requirements are an important part of this problem. Maneuvers. So a maneuver is what are you asking the system to do? Are you asking it to just not blow up, or are you asking it to do something else like track something? So that's the concept of a maneuver. This must be done in spite of an inaccurate model. So you may have a model for your system, but it may not be very accurate. So for example, with the system identification, we came up with a model, but we know that there may be some inaccuracies depending on how much noise was in the system, or if we developed the model from first principles, that is through the differential equations and physics laws and so forth, we may not know the parameters exactly. And so we have an inaccurate model of the system. And that's just a part of, we want to work with a model of a system, and yet we have to recognize that our models may have limitations associated with them. And the presence of interfering disturbances. Okay, so that's the other thing. There may be interfering disturbances for the system. All right. So in terms of our goals for the control, we have three basic goals that we're going to be concerned with. First is simplicity. Keep it as simple as possible. Next, we talk about performance, and then robustness. So these are the issues, the goals that we would have for our control design. In terms of simplicity, there are always trade-offs between simplicity and capability. How simple is the controller and how capable is the controller? Generally speaking, to be more capable, it's going to have to be more complex. Simplicity usually means it's cheaper to implement. That's the basic idea behind simplicity. To go with a more complex controller generally requires some kind of justification. The justification could be performance, overall cost, robustness. So it can be some of the other requirements of the system may require going to a more complex controller. So we're going to start off talking about controllers, very, very simple controllers. So we'll go controllers from simple all the way to complex. Okay, and so we have different ones along this continuum. Up here we have open loop controllers. Down here we have closed loop controllers. So, so the simplest controller is the static open loop controller, and so that is basically a constant gain that multiplies our system. So it basically changes the changes the DC gain, the DC value of the system. So that's static. That's a static open loop controller. We can have dynamic open loop controllers. We'll talk briefly about those. Dynamic tracking controllers, that is, we want to actually track something. In terms of closed loop, our simplest closed loop controller is the P controller. We'll talk a little bit about that today, as well as PI and PD and PID controllers. So these are all relative complexity. And then we'll talk about ripple-free deadbeat controllers. So that's the main thrust of our design approaches for this course, the ripple-free deadbeat. And so if you notice, the ripple-free deadbeat is a fairly complex controller by comparison, more complex than all these other controllers. And so if we're going to actually use this, we need to justify using it, that some of these other controllers will not suffice to do the job that we need to do. And of course, each of the controllers that we design has limitations to it. So the P, the PID, and so forth, these controllers have limitations, and the ripple-free deadbeat will also have limitations. But the question is what we can get out of this controller worth the effort of going beyond the other types of controller? So we'll also be looking at ripple-free deadbeat with tracking. The most complex, but also the most powerful, in some senses, are the state variable controls. And we're not going to talk about those. We reserve these topics for graduate classes. So these are our controllers. So in terms of performance, we have the effectiveness in performing a maneuver. We have control magnitude and energy considerations. So these are the main goals when it comes to performance. Okay, how well can we do a maneuver, and what does our control effort look like? So what are we talking about when we talk about a maneuver? Well, there are different things that we could do. So for example, a step input is a common type of maneuver. We're moving from here to here. Okay, and so that's a very common type of maneuver. In fact, this is the most common type of maneuver. We're here, we're going to go to here. So for example, if you think about cruise control in an automobile, we want to go fixed 75 miles per hour and keep that constant. That's basically like a step input. Okay, and so how does our system perform according to that step input? So 90% of all controllers, dynamic controllers, use a step input as its maneuver. Okay, so this is very common. So for example, you have, let's say, the Hubble Space Telescope. It's pointing over at this constellation. You want it to point over at this constellation. You undergo a maneuver, okay, which is like a step, a rotational step. Okay, and so a step is a very common type of maneuver for a lot of systems. But perhaps you want to undergo a sinusoid, some kind of sinusoidal motion, or some other general periodic motion. So these kind of general periodic motions are used, for example, in robotics applications where the robot always does the same motions. It always goes, picks this up, puts it here, picks this up, puts it here, and it does the same repetitive motions over and over again. And so you have your input is a general periodic type of maneuver. So it just does the same thing over and over again. We could also have, as a type of maneuver, some kind of band-limited signal. Okay, so band-limited signal means we're limiting the frequency content of that signal, and in time domain, that refers to not being able to move too fast. Okay, it's basically a limitation on how fast we can move our system. So this kind of a system would be, for example, used for a, let's say, your control system is a heat-seeking missile, and so your input then, you're trying to follow something. So it may be another missile. Okay, and the thing about that missile that you're trying to follow is it has limitations. It can't just instantly turn 90 degrees. It has to, go through some kind of arc. Okay, so, and it can't go arbitrarily fast from here to there. It has speed limitations. And so if you're trying to develop, for example, a heat-seeking missile, then but you don't know what direction it's going to go. You don't know if it's going to go that way or this way or whatever. It's going to go in whatever direction it's going to try to avoid, in fact, the heat-seeking missile. So band limited is the kind of input. You don't know what it's going to do, but you know it can't do things too radically. Okay, there's some limits to that. Now, as I mentioned, the most common type of maneuver is the step maneuver or step input. And so as a result, there are lots of quantities that are used to define, let's say a poor step response. And so when you apply a step transition, then the system does something and it eventually settles out. Okay, and so these are some examples of things that could be considered as errors or inaccuracies in the response. So the system could initially start heading the other direction. So instead of going from here directly to here, it starts heading in the opposite direction. Kind of does a Jonah. Jonah was told by the Lord to go to this place, and instead he headed the opposite direction. So, of course, the Lord brought him back in the belly of a whale. So that was, anyway, he ended up coming back. But this kind of operation or this kind of characteristic is common in systems that have zeros in the right half plane. Okay, so not poles in the right half plane, zeros. So the zeros don't affect the stability, but as you can see, they do affect the response of the system. So we also have that the system might go beyond the value that we're settling at. Okay, and so that value is called the overshoot. It overshoots the value and comes back. So you get this kind of ringing. And then the settling time is the time in which the system comes within some tolerance and stays there for all the rest of the time. Okay, so that's called the settling time. The rise time is the time it takes to go from 10% to 90% of the final value. How quickly can it actually traverse that? Okay, so there are a number of things. So in this case, the tolerance here is plus or minus 5%. That's the most common. There are other settling time specifications in terms of tolerance. But so these are some of the common, what are called figures of merit in terms of the step input. So the step input, again, is the most common, and that's why we have all of these kinds of characteristics or these inaccuracies defined. We've given them names. Okay, and so for step response, that's what we have. So those describe the performance of the system. Small settling time, small overshoot, small rise time. All of those small things indicate a better response to the step transition. We could also have a different error, for example, a sinusoidal error. And so the original signal that we're trying to track is this green one, and we could have these alternate responses. That is, we could have this blue response, in which case we end up with a sinusoid with the exact frequency and magnitude, but a different phase. Phase corresponds to a time shift. Okay, or we could have a signal that eventually locks on to our reference signal and follows it after that. So if we were to take the difference between these two signals, we would actually get a signal that looks like this, and we could check that when we come within some tolerance of 0, then we can talk about settling time for our system. We can also talk about peak deviation of the two signals. So this is the peak deviation. Okay, and so these are some characteristics when you are trying to track a sinusoid. Those are some things to look at. Similarly, for general periodic signals, we can have signals that that follow somewhat closely. You can have some signals that that have a persistent error but are fairly close. Okay, so this green one actually settles. This reddish one, it follows fairly closely, but there's a persistent error. So that the error again is the difference between the input and the output of the system. And so we can get different kinds of things happening. So in the case when we actually lock on, we can again talk about something like settling time. Okay, if we have a periodic error, it's not so easy to talk about settling time. We can also talk, so that is the maneuver. So we're talking about maneuvers, and so you talk about performance with respect to a maneuver. We can also talk about robustness. Robustness is the property of being able to handle uncertainty. So we can have, for example, modeling uncertainty. So we think our transfer function of our system is just P of S, but actually it's all of this stuff. And so the actual transfer function is given by this. It's P of S, and then it has some other stuff here in the denominator. Okay, and so this is our actual transfer function. And so notice that the uncertainty appears primarily in the denominator here. So this is just one model of uncertainty. This is called multiplicative uncertainty. This is one type of uncertainty. And if you have an uncertainty that has or a system that has uncertainty in the denominator, we can draw, or we can express it this way. And if I take this equation and solve for u, I get in terms of this. So in this case, u is described by the percent difference between the actual system and the nominal, or the system that we think it is, divided by the actual system. Now, I don't know what the actual system is. It's uncertain. But we can define the error, the percent difference, this way, in which case the u actually appears in a form that looks like this. So it actually has a physical meaning. So even though it looks kind of weird, it's like, why would you put the uncertainty this way? Well, this is why. Because we're casting the uncertainty as a percent difference in terms of the transfer function. Okay, so this is just one way of modeling uncertainty. So there are other ways of modeling uncertainty. So if you have now an uncertain model, so this is my plant, it's uncertain. If we design a control system, wrap a control system around that feedback, we get a closed loop transfer function an actual closed loop transfer function, and we have it now, our uncertainty now is different. Our uncertainty now, again, is the percent difference of the actual closed loop system with the nominal closed loop system. And so we can see that the closed loop transfer function has a different uncertainty. And notice now the uncertainty of this system is a function of the controller, in particular of controller 2. So this has controller 1 and controller 2 here. So it's possible by appropriate choice of controller 2 to make this uncertainty small. So this is one of the reasons for feedback, is that we can actually deal with things like uncertainty. So, but the uncertainty still is there, but its impact can be made possibly small. So when we talk about robustness, one aspect of robustness is, or rather the flip side of robustness, is fragility. And in particular, it asks the question, how close to being unstable is the system? So here's a loop. Okay, here's our plant. We have a controller. So this is like a sensor transfer function. Okay, and so we have this loop gain that includes all of these transfer functions. Okay, and the question is, how large can the loop gain be before the system becomes unstable? So let's suppose we've designed a controller so that takes into account K and H and C. So for example, we would have chosen a C to control a system that had a K and an H. The K, for example, might be a power amplifier. The H might be a sensor that has its, and each of these have their own transfer functions. And now we're designing a controller to control all of that. So suppose we've designed a controller to make this thing stable. Then the question is, how large can the loop gain be before the system becomes unstable? So based on that, we can define something called the gain margin. The gain margin is the gain at the phase crossover frequency. So the phase crossover frequency is when the loop gain has phase 180 degrees, or plus or minus 180 degrees. Usually it's minus 180 degrees. And so the frequency at which that occurs is called the phase crossover frequency. That phase crossover frequency then is used to determine the gain margin. That's the gain at the phase crossover frequency. So this is a measure. In the same way we saw measures of performance, like overshoot, settling time, rise time. Those were measures of performance. Here we can talk about measures of robustness. So this is one measure, okay, the gain margin. It's a very common measure of uncertainty, or rather stability, fragility. Phase margin is another quantity that can be used to specify robustness. So the phase margin is the phase at the gain crossover frequency. So the gain margin was the gain at the phase crossover frequency. Phase margin is the phase at the gain crossover frequency. So there's obviously some crossover between gain and phase in all of this. And so this is the formula for the phase margin. So it involves the phase of the loop gain at the gain crossover frequency. The gain crossover frequency is the frequency at which the transfer function, the loop gain, has magnitude 1. Okay, so that's the gain margin and the phase margin. And so we talked about these in EE 314, and we've also talked about how to actually compute the phase crossover frequency and the gain crossover frequency. Basically, it involves computing roots of polynomials. And so we have a polynomial like this. We're looking for the purely imaginary root, or a purely imaginary root of this. So if there's a phase crossover frequency, it will occur at a purely imaginary root of this polynomial. The gain crossover frequency will occur as a root of this polynomial. So you notice here I have the numerator of L, the denominator of L, and so here we have d subscript L of minus s. Here we have d subscript L of s. And so we have n and d here. Here we have d and d, n and n. Okay, so these are different polynomials. They compute different things. Okay, so we can go through and establish that these are in fact ways of computing those frequencies. So we now have ways of examining stability and robustness for these systems. Okay, now we're going to actually look at some the simplest control designs. And so we're going to start off with the minimum complexity, or rather the maximum simplicity, the open loop baseline. And we're going to talk about the open loop static design, the dynamic open loop. Okay. Then we're going to go on to the simplest closed loop, which is the P controller. And then we're going to talk about a more complex controller, the PID controller. So we're going to talk about all those designs in this presentation. So we still have a little bit more to go here. So the important thing here is that we're giving you some simple baseline design so that you have some tools to begin comparing in terms of simplicity and complexity. So the simplest design is open loop, and in open loop we used what's called the principle of inversion. That is, we invert the relationship between the input and the output in order to determine what input is needed to obtain the appropriate output. Did you get all that? So we invert the relationship between the input and output in order to determine what the input is needed to obtain the appropriate behavior. So for a static open loop controller, this is our controller. Here's our system. We have a gain, and all we do is we just cascade that gain with the system, and that is how we choose our gain. We choose our gain so that we have the DC gain equal 1 of this entire system. And so we choose the gain K to be 1 over the DC gain of the system, which is 1 over the transfer function evaluated at 0. So if you think of 0 frequency, that's DC, and so 1 over the magnitude of the DC gain is going to give us a zero steady state error when we do this. When we talk about steady state error, we mean that this will settle out to the value 1 if this is a step input. Okay, so it's a unit step. Okay, so we can also consider open loop inversion, the static open loop inversion for a sinusoidal input. So if our sinusoidal input is given by this, then we would choose the gain k to be 1 over p at 1 over p evaluated at j omega. Okay, so notice that when we do this, we do not get zero steady state error. In fact, only the magnitude will match for a gain chosen by this. Okay, so that's all there is to the static open loop controller. So notice that in order to obtain this controller, we need to have a model of our system. Okay, we need to have a model of our system, and yet we do not need to know the entire model of the system. We only need to know the DC gain of the system. So we actually don't need a lot of information to design this controller if all we're doing is do this. Okay. We also notice in this we require that the system, the plant, be stable. So you can't just do any system. So we have these limitations. The controller must be stable as well. Oh, that's the next thing. So the plant must be stable here in order to be able to do this. Okay, so that's the static open loop control. Let's move on to the dynamic open loop control. Again, we're going to do inversion. So it's important that the controller be stable. So the system must be stable, the controller must be stable. Now it turns out that for some systems, if you have an unstable system, you cannot make it stable. You need to make it stable. An open loop controller will not make an unstable system stable. Okay, so the controller must be stable. The controller must be realizable. That is, it has to be causal. So in terms of transfer functions, a transfer function in the Laplace domain is causal if the order of the numerator is less than or equal to the order of the denominator. Okay, so in designing a controller, the controller must be realizable. Again, we want to make the controller as simple as possible, and the controller must be able to do the job. So an example of the form of controller is this. We have some model divided by the plant. So basically, when I put this and cascade this with the plant is going to cancel. So this basically requires that we have a stable plant and also that the zeros of the plant are in the left half plane, not in the right half plane. We also require that the degree of m equal the degree of the transfer function. Okay, so we have these requirements that are a consequence of this. And we can actually have modified forms of this. That is, we don't have to cancel the entire plant. We can cancel parts of the plant. Anyway, there's certain things we can do to actually make the controller simpler. So if we want it to be as simple as possible, there are ways to make it simpler. So if we want to track a step input, for example, if we want our system to track a step input, then we would use a model. Again, the plant must be stable. The plant zeros must be in the left half plane. The relative degree of the model must be equal to the relative degree of the plant. So the relative degree of a transfer function is the order of the denominator minus the order of the numerator. Okay, so that's the relative degree. And so here is a usable model. Some constant to the power nr, where nr is the relative degree of the plant. Okay, divided by s plus a to the power nr, where a is some constant. So this model has 0 overshoot, 0 steady state error, and a settling time given by this. So if we need a particular settling time, this also has 0 overshoot. 0 overshoot. So if we need a system that has 0 overshoot, we have that, 0 overshoot. So the settling time is related to the order of the transfer function also divided by the whatever value of a we choose. So by appropriate choice of a, so notice that we can make this quantity as small as we want. Okay, so if we make a larger, that will make this smaller. Okay, so based on this, then we have a model that can be used to track a step using open loop design. Okay, it's of this form. So that's all there is to it. Again, it's simplicity. So the complexity is that we actually have to implement some arbitrary transfer function like that. Open loop tracking with a sinusoid. So if we want to track a sinusoid, these controllers will track a sinusoid with 0 steady state error. So again, it uses a controller of this form where it has the model and the plant. So the plant is going to be canceled, and the model is given by this depending on the relative degree of the plant. Okay, so these will have the appropriate. So this has relative degree 1, this has relative degree 2, so forth. Okay, and so notice that this controller is a function of both some parameter A and the frequency W, frequency of the sinusoid. And so you can choose A roughly of this form to satisfy this kind of a situation. So this is a rough approximation of the settling time for a given value of A and relative degree. So that roughly applies. It's not perfect, but it gives us something close. So now, how does open loop controller compare with closed loop control? Well, they're different. They're different. So one example is we have the problem of filling up a tub of water. So here's an open loop control approach. We turn the water full on, we leave it on for t seconds, then turn the water all the way off, where t is equal to the desired volume divided by the full on flow rate. Okay, so that's the approach that we use, and so we just let it turn on, and then when it's done, we shut the valve off. Okay, so that's the open loop control. Now, closed loop basically requires measuring the actual water level and adjusting the flow rate proportionally. So the flow rate is some constant times the desired level minus the actual level. So when the actual level reaches the desired level, the flow rate goes to 0. And so we're just continually doing this. Okay, so this requires continual monitoring of the water level. And that requires a sensor. You actually have to measure the water level. So often the sensor is one of the most complicated parts in the entire system. So that's why closed loop control is more complicated than open loop control. It requires a sensor. So the difference now is that if something is off about the system, so for example, let's suppose we designed an open loop controller to fill up to a certain level, but that level is predefined before someone gets in. And so when someone gets in, it could actually overflow. Whereas the closed loop control, it's constantly checking the level, and so it will not overflow. So if the person is in the tub when the thing is filling up, it could overflow. If the person is in the tub when the closed loop control is action, since it's continually checking the water level, it will not overflow because it will stop at that level regardless of whether someone's in the tub or not in the tub. Okay, so this is some comparison. So further comparison of open loop and closed loop control. In terms of complexity, the open loop control is simple. Closed loop control is generally more complex. It requires sensors. In terms of stabilization, if your system is unstable, open loop cannot stabilize, whereas closed loop can stabilize. In terms of performance, you can get fair performance out of an open loop controller. So the controllers that I've just shown you, the dynamic controllers in particular, can give a pretty good response. So again, it requires, there are some certain limitations. So for example, if your system is unstable, you can't even use the open loop controller. But if it's stable, you could actually get a fair response. Performance. In terms of closed loop, you can achieve optimal performance. Okay, so that is, when we say optimal, that's the best according to some measure. Okay, in terms of disturbance rejection, suppose there's a disturbance entering your system. Well, the open loop control really cannot do much about disturbances. Okay, it just cannot do that. Whereas in closed loop control, we can actually achieve optimal. That is, minimum impact of the system with respect to disturbance. What about robustness? What if our system isn't exactly what we thought it was? Well, the open loop controller can't do anything about that. You design a controller for a plant, but if your plant isn't exactly what you thought it is, you might get very poor performance as a result. For closed loop control, you can achieve optimal performance or robustness. So this can handle uncertainties. Well, let's look at a couple of examples of this using feedback control. So here is our system. This is, or rather, this is what we desire. Our input gets multiplied by a gain of 1 and gives the output. That is, it basically does a unit conversion, a perfect unit conversion. So, for example, this input to the system might be voltage, the output might be position. Okay, or the input could be, let's say, the throttle or a numeric entry, and the output is the speed of your vehicle, and there's just a one-to-one match. Okay, so suppose this is what we have, but suppose this is what we want, but we actually have this. We have something that has a large gain, and we have uncertainty appearing, where the uncertainty is 0.5, which means this part of the system has a gain that's anywhere from 0.5 to 1.5, depending on the value of delta, the uncertainty. And as a result, this overall thing has a gain between 50 and 150. Okay, so that's a big difference. So this is what we have to and it's like, well, why don't we just start with something like that? Well, the thing is that you're doing a conversion here. So there's something that's changing the physics of the system, so that, for example, this is voltage and this is position. You've undergone a conversion, so you can't just you can't always just do that. So this thing does that conversion, but it does it inaccurately. Okay, and so how would we recover from this? So if we apply a closed loop system, in this case this is actually a P-controlled system where the gain is 1, we can look at the transfer function of this system. Okay, the transfer function of the system is given by this, the closed loop transfer function, so you can go through and show that. And I can simplify this down to this, 1 minus this quantity. So what does this quantity look like in terms of size? So I'm going to call this delta tilde, or delta closed loop. And so here's what we have for delta tilde. All right, so for delta between minus 0.5 and 0.5, delta tilde is between 0.00662 and 0.01926. And so this quantity, 1 minus delta tilde, is between 0.98 and 0.99. So notice that these two values are within 2% of 1. So we wanted something that gave us exactly 1. We didn't get something exactly 1, but we got it within 2%. So instead of being 50% off, we are now 2% off. So we've drastically improved the accuracy of this whole situation. So this whole power amp problem. Okay, so in terms of how this might look in a simulation, okay, in terms of simulation, this is the kind of thing we have. So we actually are comparing 4 different controller designs for this system, 2 open loop designs, and here these are 2 closed loop designs. Okay, so the 2 open loop designs are at the extremes of the uncertainty. Okay, so the extremes of the uncertainty, we have, remember, plus or minus 50% uncertainty. So this is minus the uncertainty. This is positive the uncertainty, and we do the same thing here for the closed loop design with minus uncertainty, positive uncertainty. So we're actually doing 2 simulations for each case. So for the static open loop and for the P controller. Okay, and so when we actually look at the traces, the signal traces, we have the reference signal, which is a sine wave. Okay, and so here what I see are what looks like 3 plots, and there's some overlay here. So the yellow is actually this top plot. The purple is the next one. So that's these 2 guys. So this yellow has the minus, and then the purple has the plus, and so you can see they're significantly off. In fact, it's still 50% off in terms of, if you look at the peak values, 50% off. This is plus 50%, this is minus 50%, so it's not doing that well. The next three is the actual reference signal, and then the two designed using the PI controller. And you can see all three of these guys are very close to one another. They're within 2%. And so we can see that using feedback control has given us a fairly accurate response to our system. Okay, so there's our power amp problem. Our second example involves the use of disturbance rejection. So again, we want a plant that is basically 1, but instead we have a disturbance entering our system. We have a disturbance entering our system. Okay, and I'm going to assume for now that our G is equal to 1. It's just 1. But we have a disturbance entering our system. So as far as control is going, I'm going to use a closed loop control with a gain K here, and I'm going to close the loop. And so when I close the loop, this is what I get. K over 1 plus K plus 1 over 1 plus K. So this is times R, our reference signal. This is times W. And so when K is equal to 50, this equation becomes 0.98 times R, 0.196 times W. So what's going on here? What is this actually telling us? Okay, so Y compared to R is basically 0.98. It's within 2% of 1. And so that's what multiplies R. What multiplies W is something very small. It's like 2%. Okay, and so if you look at our original system, it was R plus W. And so the signal to noise, so here's the signal, R, the noise is W, signal to noise ratio is 0 dB. So if I take this signal divided by the noise, I get a dB of, I get 1. When you convert 1 to dB, you get 0 dB. If I take this value divided by this signal to noise ratio, and I convert that to dB, I get 34 dB. So I have drastically improved the disturbance rejection by this feedback control. So to look at see what that looks like in terms of simulation, here's our sine wave. Okay, and again we have band limited white noise. That noise affects this system, and it also affects this system. Okay, and so this is our system. And here I'm using the feedback control. Here I'm just using, here's the original system. Okay, and so then I'm also showing the original reference. So the yellow plot is this signal, the purple plot or magenta is this signal, and then the cyan or the blue-green is this signal. And so you can see the yellow signal, that's the signal with the noise. Okay, there's a lot of noise in that. The magenta signal is right around, so the cyan signal is the actual sinusoid. The magenta signal is the output of this system, and you can see it's a lot less noisy than the original signal. Okay, so we have drastically reduced the noise by using feedback. So that's helpful. Okay, so basically a high gain controller has lots of benefits, and so feedback helped to reject the noise in this particular problem. Okay, so these two designs basically involve the use of a P controller, and this shows that even the simplest feedback controller, the P controller, proportional, the simplest can do some things that an open loop control could not do. Now, sometimes a P controller isn't able to do the job. It's just not complicated. Doesn't have enough flexibility to do what needs to get done. the P controller, for example, cannot, in general, provide zero steady-state error for a step input, for something simple. Okay, so as a result, the PID controller is often used, and it's actually used in 90% of all control applications, the PID controller, or some variation. It could be a P controller, PI, PD controller. The use of the PID control could actually be an institutional constraint. So in some companies, they buy these boxes that do PID control, and they just want you to use that box because they use that box everywhere, and they like that box, and so they want you to only use that kind of box to do your control design. So in that case, you're stuck with a PID control. But and the PID is actually fairly robust in that it is non-recursive, so it has certain built-in features associated with it. There's a lot going for it. So here's our PID control design, what it looks like. So we have our plant, gets fed back to form an error. The error then gets multiplied by a proportional gain. It multiplies by gain divided by S. So this basically is an integrator, and then it has a gain times S. So this is the differentiator. So proportional integral derivative is what PID stands for. And then the overall control signal is the sum of these three signals. So the PID controller is nice in that it only has three gains to tweak, and it's simple so that it can be tweaked by anyone, including a technician that's working with the system. So if the system has trouble in the middle of the night and they need to retune the controller, the technician can tweak those gains a little bit. They can be very skilled at developing understanding of what happens when you tweak this, what happens when you tweak that. And so it's simple. It can be tweaked by anyone. You don't have to know differential equations or Laplace transforms. You don't have to know any of that to tweak a PID controller. Each of the gains has a different effect on the system. And basically, the controller satisfies what's called the internal model principle for a step input. So that's why it's able to track a step input with zero steady-state error. Okay. So in terms of the design of a PID controller, we have this is the form of the transfer function, Kp plus Ki over S plus Kd times S. If we put this all over a common denominator, we basically have a quadratic polynomial in the numerator divided by S. So we could factor that quadratic polynomial into two roots times a constant gain. And so basically the controller has a pole at the origin and two zeros. And so the two zeros can be placed, and then the Kd can be chosen using a root locus tool, for example. Once you have the two zero values chosen and the gain value, we can work backwards to find the Kp and the Ki. And so this is how we would design a PID controller. So in EE314, we talked about this. We use root locus, for example, the RL tool in MATLAB to do this kind of control design. So that's the analytical design of PID controllers. There are also empirical methods for doing PID design. So in the empirical methods, we do a simple experiment. So for example, these two methods involve a step response. You apply a step response to the system, you look at the output, and based on features of the output, you have a design for the controller. And these design methods are fairly straightforward. And so again, I talked about these in E314. I'm not going to talk much about them here. Then there's also a frequency response method that can be used. So again, this involves another experiment. This one, for example, actually uses a P controller that you tweak until the system is on the boundary of stability. That is, you get a sustained oscillation going in your system, and based on that, then we can design a controller. So this is the empirical design. And again, I'm not going to go into great detail about this. I talk about this in E314. And I'll probably just go ahead and reference those videos if you want to check more about the actual details of these. So this lecture is an introduction to feedback controls. We're looking here at the most basic form of the feedback controls. Then we're going to get into actually using the sample data control and feedback using the ripple-free deadbeat control. But we look at what we've talked about here as a basis of having something to compare. Okay, so if what we're doing is not better than some of these basic designs, then we have to question the wisdom of doing what we're doing. So this is the basics of feedback controls. Thanks for watching.